Now we'll examine a standard normal distribution. What's important about this section is the idea that we can take any random variable x, so for any normal distribution. These distributions have a variable of x, like a specific x value, but that value is normally distributed with some mean. That's some number specific to that distribution, and so is the standard deviation. We can take that. So here's the example I use in class. There's this distribution in blue, and then there's a distribution in green. So let's compare the two of them to each other. You could think of them both as heights. They could be heights of males and heights of females. Because we have two different populations there, we would not be surprised to see two different means for the heights and a different spread for the heights. So in class I ask all the students to calculate their height in inches and then say where they would lay on the curve. Like if you're a female, above average, below average, what's your actual height? And for the males, where's your height relative to your own curve? Now, that's a normally distributed variable specific to that situation, female heights and male heights. In this section, we're going to take that normal distribution, that any normal distribution, and transform it into what we call the standard normal distribution. Where the variable is now z, and the mean is 0 and the standard deviation is 1. You see that indicated here on the curve. The mean is 0, the standard deviation is 1, -1, or 1 standard deviation from the mean where we have the inflection points. So that's a transformation. We can get there by taking all the x values, subtracting the mean of that population, and dividing by the standard deviation of that population. We do that for a population, or you could do it relative to sample data if you like. The formula is the same, where mean, mu, and x bar mean the same mean, either from the population or the sample, and this population standard deviation sigma, or s, for the sample standard deviation, are both standard deviations. What this value z does is measure the number of standard deviations the x value is from the mean. So that makes everybody relative to the same point, if that makes sense. This new distribution z says we're going to compare female and male heights not to their respective distributions, but to their distance from the average in terms of standard deviations for their populations. That's a normally distributed variable, still the same shape, still normally distributed, but now the mean is 0 and the standard deviation sigma is 1. So we can make that transformation. In section 6.1, we saw how we could take a normal curve and we can move it up and down the x-axis by changing the mean. Now we moved all these different specific normal distributions to a mean of 0 by subtracting the mean from each x value. And then we force the spread to match the standard normal distribution by dividing by the standard deviation of the population. Here's an example with refrigerators. So refrigerators are normally distributed. There's a mean of 14 years and a standard deviation of 2.5 years. If I draw the distribution and jump to part B just to give you a picture, the specific distribution, mean of 14 years, 1 standard deviation away, would be 2.5 years larger, 16.5, or 2.5 years less than the mean, 11.5. So there's the distribution for the x value, where x is the lifespan of a refrigerator. The standard score, or what we call the z-score, of the refrigerator is z equals the x value minus the mean divided by the standard deviation. The x value in this problem is 16. The mean earlier is 14. The standard deviation is 2.5. So that's 2 divided by 2.5, or 0.8. That's the z-score. right? The variable is z, so the answer z is 0.8. The distribution, the standard normal distribution, always looks the same. Always normally distributed, always a mean at 0, and a standard deviation of 1. So 1 and -1 are the points of inflection on the curve. Now this is a z, where z is the standard score for lifespan of refrigerators, just from our application. If you look at what we would plot, the x value, x of 16, would be right here, just shy of that first standard deviation. Or we could plot this z-score. The z-score is 0.8, just shy of that first standard deviation. But now they're just different numbers, relative to the standard score versus relative to its own distribution. So what we'll practice in this section a little bit is transforming x to z, and then interpreting the z values from there. So look at the next example. PE department offered a first aid course. The scores on the final were normally distributed, and they give us the z-scores of the distribution. So Robert didn't score 1.1 on his test. He has a z-score of 1.1. To determine which students score above the mean, those students will have positive z values. That's Robert, Juan, and Linda. They scored above the average because their standard deviations are larger. They're positive z-scores. Then below, students who scored below average are Susan and Jan. They have negative z values. That means that Jan was negative 0.8 standard deviations from the mean. Susan was negative 2 standard deviations from the mean. She was 2 standard deviations below the mean. Joel did not have a positive or negative value. He was scoring exactly on the mean. Not a score of 0, but a z-score of 0. Means that he got the average value for that test. The most extreme score is the one that's the most or the farthest or the largest in absolute value. That means they are farthest from the mean in terms of standard deviations. And that winner is Susan. She didn't do well, she did poorly, and she did the most extreme in the poor direction. You can see things like this when you want to compare situations from two populations, like in competitive running or triathlons, where we have different brackets, like people who are professionals, people who are amateurs, men versus women, people who've done it before. We have all different kinds of brackets when we compete in a physical competition like that. And so while one person's time might be longer, relative to their group, they might have done better than another person with a shorter time. So by comparing them in the standard score, we take out like the variability due to the population difference, and then we can compare who did better compared to their own group. So that's an application of where we do this. Now the next idea here is how to find areas under a curve. So if you'll remember, the normal probability density function was pretty ugly. Y was 1 over sigma times the square root of 2 pi e to the minus x minus mu squared divided by 2 sigma squared. Quite freaky, and no one really wants to mess with that formula. So what happened was we said for the standard normal, when the mean is 0 and the standard deviation is always 1, we're going to plug those values into this formula, and we're going to calculate values for that formula once and for all time. Just record it in a table just like this, and then we just have to look it up later and not recalculate. So if we're asked to find areas under the normal curve, we can look them up in Table 5, shown here in part, by finding the z-score of interest, the first 2 digits are in this first column, so like z negative 3.4, negative 3.3, negative 3.2, and then the last digit, or the hundredths place, is this first row. Once you find the z-score, you find the intersection of the row and column. First two digits tell you which row you want, hundredths place tell you which column you want, and then you can read the appropriate area. From the table. If you've taken statistics before, or you just Google a z-table, they'll all have values inside. They'll be set up like this, but the one very important thing to notice is the key or the legend that tells you what the table areas are from, where they're from. So here we have it noted twice for us. The areas in the table are to the left of z, area in the table is to the left of z, and then even a nice little picture that says, look, the table will give you areas for this blue area shown in the picture, which are to the left of z. So different tables might show you values from 0 to z or from to the right of z, so make sure, because that makes a huge difference in what you're trying to find or how you'll use those numbers. If you just want to use the one from the book, you can print this off of e-learning. You can always reference it from the book. It'll look exactly the same, and that guy always tells you area to the left of the z value that you look up. So let's do it. If I have a z value of negative 3.25, I need these first two digits will tell me the row that I need. So I read down until I find 3.2. That would be this row. Negative 3.2. There's a lot of options for that hundredths place. That hundredths place here is a 5. That tells me which column to read. So I want the 0.05, because if I put those two numbers together, I get the right z-score, negative 3.25. And the intersection shows that I have an area to the left of this z value of 0.0006. That's how I've read the table. It's very easy when the values are right to the left, funny. If they are just to the left of the z value, and that's what the table gives you, we read it directly from the table. So for z equals 1.55, I'll pull up my expanded table here. Now the z value is positive, so I need to find on the left where I can get 1.5. Here I have 1.5, but it's negative, so it won't give me the proper value. If you flip your table over, if you printed it on two sides like I do for my class, now we have positive values of z, or the picture still shows area to the left of z, and we want this row, 1.5, and we want a hundredths place of 0.05 as well. That makes 1.55, so I'll find the intersection of those two, and I get 0.9394 for the area to the left of 1.55. When we're looking for area to the right of a curve, but our table gives us area to the left of a z value, we have two options. We can use symmetry or the complement rule. Symmetry works like this. The curve is symmetric across the mean. So if I know the area to the left of some negative z value, by symmetry, this will be the same as the area to the right of the positive z value. If they have the same z value that are only different by a negative sign, then the area on the extreme side, either to the left of the negative or to the right of the positive, will be the same. That's because the curve is symmetric. So if I look at this 3.25 curve, I have a normally distributed variable like this. 3.25 is somewhere over here. It's a positive value, so it needs to be larger than the mean of 0. And I want the area to the right of positive 3.25. Now earlier in part A, we found the area to the left of negative 3.25 to be 0.0006. So left of negative, because if I just folded this curve across the same 0, I'd get exactly the same area to the right of the positive version. So the right of 3.25 is 0.0006. We can also use the complement rule, which in general will say, looks like this. If you want to find the area to the right of some z value. So this z value could be positive or negative, doesn't really matter, but I want the area to the right here. But the table gives me the area to the left of the z. I use the fact that area under the whole curve is 1 and subtract the area that we can get from the table, which is to the left. So 1 minus the area to the left must give us the area to the right. A good example of using this is when we have negative 2.33. That z-score is negative, so he's to the left of the mean at 0. I want, though, the area to the right now. So what is this area is the question. But the table will give me this area. So the table value of 2.33, we can look up. Negative 2.33, excuse me. Negative 2.3, so I'm on this row. And 3 is my hundredths place, so I have 0.0099. Negative 0.0099. So the leftover, the green area, will be 1 minus the blue area from the table, 0.0099, for an area of 0.9901. Must be the area to the right. That's by the complement rule. Now if we look for symmetry, we would do it by finding the table value of the positive 2.33. That's the area to the left of the negative value. And that should be the area to the right of the positive. So let's look up positive 2.33. Positive 2.3 is here. And 3, this column, 0.9901. So that was a direct read from the table, but I had to change the sign from negative to positive to read it from the table because I was looking for area to the right. So understanding what your table gives you and what you want is really the key here. C and D, again, the answers are posted in the lecture notes if you want to try it out yourself and then check your answer. You can do that. They get more complicated when we're trying to find area between certain values. So this really means that you need to understand what the table gives you and what you want. In this case, this part A, the curve is symmetric and I have symmetric z-scores. So I'm looking between negative 2.55 and positive 2.55. And I would like the area that's right in the middle of those two values. The table will give me area to the left of any value, but not area like only from 2.55 to the left of 2.55, but to the right of negative 2.55. So what I like to do here is take the table value of 2.55, that's the area to the left of 2.55, all of it from negative infinity to 2.55, and subtract the table value at negative 2.55. The stuff that is to the left of negative 2.55, that would be some overlap, and I don't actually want that piece. So that's a way to do it. Let's find the value of the table at 2.55. To the left of 2.5, which is 5 is my column here, is 0.9946. Minus the area to the left of negative 2.55. This is my row, and my column is here, 0.0054. Gives an area between the two of 0.9892. That's taking the area to the left of the rightmost value minus the area to the left of the leftmost value. Now another way to do it, because it's symmetric, and this is a special case where the z values are just opposite signs of each other, we could use the area in the table to the left of negative 0.255. We read this to be 0.0054. And use the complement rule in conjunction with symmetry. So if left of negative 2.55 is 0.0054, to the right of positive 2.55 is 0.0054, then the area in the middle is 1 minus these two tail areas. This is by symmetry and the complement rule. That first approach, approach A, will work every time. Table value of the right value minus table value of the left value. That's a good deal. Or B works only in this special case where we have symmetry. But it might be more faster for you. It might make more sense. Whichever way works for you is really the goal, just to arrive at the right answer, right? And particularly one that you understand. So this next case, 1.67 and 0. So we want to be between 0, which is right in the middle, and a positive 1.67. We can use the general approach A, table value of 1.67 minus table value of 0. The table value of 1.67 minus the table value of 0 is the value at 1.67, 0.9525, and the value at 0 is 0.5. Maybe you didn't even have to look that guy up in the table because it's symmetric. Area left of 0 would be half, and the area left over is 0.4525. This is not a special case, it's not symmetric, so we can't do option B where we take the area in the tails and multiply them by 2. You could find the area in the tails and subtract them from 1, they just won't be the same value. Again, part C, if you'd like to do it yourself, you can. The answer's in the lecture notes. And the last way we can do this, we've done to the left, to the right, and between two values are to be on the outside of two values. So remember, the table still tells you the same thing, it's just manipulating the answer you have to get the value you want. We want to be to the left of negative 2.55 and to the right of 255. We want, this time, the area in the tails, which was the area we did not want in part A of number 5. So left of negative 0.255, right of 2.55. This guy is a direct table read. The table value of negative 2.55, we already said, we found that earlier, was 0.0054. By symmetry, we know exactly the same value over here because it is symmetric. It is symmetric because the numbers are the same. So this table value is also going to be 0.0054. Excuse me, not the table value, but the value of the area to the right of that. So the total area would be twice 0.0054 or 0.0054 plus 0.0054 for a total of 0.0108. Again, it's faster if it's symmetric. If it's not symmetric, we have to do a little bit more footwork. To find the area to the left of 1.31 and to the right of 1.93 requires we look these values up in the table for sure. Left of a value is very easy to find, right? So this guy is directly, we can already find this area by looking 1.31 up in the table. It's simply area to the left of 1.31. By doing that, you'll find that the area is 0.9049. The area to the right of 1.93 you can find in two ways. You can do the complement, 1 minus the area to the left of 1.93, or you can use symmetry. I like to use symmetry if I can, so I just have to read one value and not have to make any subtraction. So I'll look up in the table negative 1.93 because the area to the left of negative 1.93 will be the same as the area to the right of negative positive 1.93. That area to the left is 0.0268. So together, the area of these two tails is 0.9049 left of 1.31 plus 0.0268 to the right of 1.93 for a total of 0.9317 for the area on the tails. Part C you can try out yourself, compare it to the lecture note answers that are posted in e-learning and see how you're doing to assess how you can do this. Now the next section, we take section 6.1, put section 6.2 together, and we actually answer questions about probabilities there. So we're kind of getting the pieces. It might not make total sense right now what we're doing, but in the next section we'll put it together and see what it actually means to us.